Today, we are finally trying to match our macroscopic description with every single time I've said, well, actually, the atoms are doing this, or maybe this is how the atoms behave, or something like that, right? We're trying to combine these two descriptions and trying to make them meet somewhere in the middle so that no matter what way we try to describe our gas, we can still accurately describe what happens with the actual behavior, right? So, today's the day. First, think back on all the stuff that we've seen from the macroscopic view of gas. We talked about state variables and the number of moles, pressure, volume, temperature, thermal energy. We talked about work being done by this thing, and this is still a useful description. We're certainly not going to leave this behind. And when we go into chapter 21, we're actually very much going to prefer the macroscopic description because it's honestly really easy to use. It's really useful. It's got really great descriptions for things like work being done, which is very useful for heat engines, which is why we prefer it in chapter 21. But it is still important to look at the microscopic view of things because that really tells us how we got here, right? We know that gases are made up of a bunch of individual particles. We just haven't talked about it like that so far. So it's good to kind of have the roots of where does this actually come from? Can we justify this maybe broad description that we have used so far in the macroscopic region, right? So remember, these are some of the variables that we haven't used in a little while. But if we're talking about some sort of gas that we've got, then that gas is made up of a capital N number of particles, and each particle has a mass lowercase m. Right? And I've kind of described this before, but these are particles. They are just masses, so they behave like what we have seen before. They're a bunch of little things flying around and obeying all of Newton's laws, for the most part. For our purposes, they obey Newton's laws perfectly. No weirdness going on here, no wave-like motion. These are indeed particles. So, how do we marry these two descriptions? Well, first, we've got to spend a little bit of time talking about what's going on with these microscopic particles anyways, right? So the first thing that I want to introduce here is what we call the Maxwell-Boltzmann distribution. See, when I keep talking about all of these particles that are bouncing around in every which way, the reality is that they're not all moving at the same speed, right? They're actually moving at a variety of speeds, and when you go through the lab that is associated with this lecture, you will find that same thing. If you actually watch these things, that some particles will be moving very slowly, some particles will be moving very quickly, a lot of them are somewhere in between. It's really a distribution of speeds, and it follows the Maxwell-Boltzmann distribution, right? So it is this very, 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 very nasty equation. There's not a prettier way to write that, right? It's really kind of crazy. That whole thing out front here, this 4 pi n m over 2 pi kBt to the 3/2 power, that's all actually just a constant. Once you find the number of particles, capital N, you just kind of leave that one sit, and that's some sort of scaling constant for the distribution. The part that actually gives it the shape is the second half, so v squared times e to the negative mv squared over 2 kBt. Right, which actually looks a whole lot like this whole thing right here, just with the v squared as well. So it gives us this kind of wacky distribution, right? So the very beginning of this thing, where if I'm plotting out the total number of particles versus what that velocity of the particle would actually be, towards the very beginning here, the v squared actually dominates, so we see mostly a parabola. Then we hit kind of a turning point, and the exponential decay starts to take over. And what we end up with is this really, really, really long tail, right? So there are a few of these particles that are moving at crazy high speeds, but they're very, very few compared to the rest of the distribution. Now, here's kind of a point that I really need to make, and I'm going to hammer on this a couple times because it's a little bit strange. If I was to take one particle, and I wanted to pluck one single particle at exactly 200.0000000 meters per second. Am I going to be able to find any such particle? Not really, right? To find any sort of exact velocity is not actually realistic. This is a distribution, and at the heart of any distribution is a certain amount of binning, or a very tiny range. So what I'm much more likely to do is ask how many particles am I going to find in this distribution that have a speed somewhere between 200 and 201 meters per second. Because really, if I was to really just say 200 on the dot, think about how wide that actually is. To find any number of particles here, right, this is actually some sort of distribution like this. This is my plot of n, but to find any sort of real number of particles, I have to take n dv. I have to find the area under the curve. And so if I limit myself to a single point, which some of you may know as a delta function, what's the area under the curve of a straight line? It's infinitely small. I'm not actually going to find a particle there. So I have to give it some range, some d of v, right? I've got to do a little bit of binning. I've got to open up a tiny bit of a range, and now there's some real area under the curve, and I can actually calculate how many particles would be there. But until I do that, right, the likelihood of finding something exactly 200 on the dot, it's just not going to happen. You've got to open up some sort of range if you want to find any real values. So, let's talk about some statistics, right? We've got three things that we might be interested in finding. First is the most probable speed. And that's actually the easiest one. If I look at this graph right here, I say, okay, well, what's the most probable speed that I could possibly have? It's wherever the most particles are, and that is right at the top, the highest point. The second is just a statistical average, right? I'm sure you've seen averages at some point or another. This is no different than an average. This is just a really clean way to write out averages. The last one, though, I've got it highlighted because this is probably a new one, called the root mean square. What this is doing is not finding the average of the velocity, but it's essentially finding the square root of the velocity squared, which sounds like I'm just getting back to velocity, but take a closer look at this. If I imagine that the average speed is essentially it's a weighting function, right? Where it's saying, okay, well, I weight every particle by what its velocity is or what its speed is. And then I sum up all of those things, I divide it by the total number of particles, and I've got an average speed somewhere right in the middle. When I do this for the root mean squared, instead, what we're doing is we're taking velocity squared as the weighting factor. So we're taking velocity squared as the weighting factor and multiplying essentially every particle has its speed squared, weight by that, and find the average of that value. And then take a square root so that we come back to a similar value to the average speed. And this sounds like a bunch of nonsense, right? I know it does. It sounds a little bit strange. It sounds a little bit tedious. Why, we already took what looks like a complicated function and we made it even more complicated. But it's got its uses, right? And on the equation sheet specifically, we use VRMS a lot more than we use VAverage. I'll go off on a tangent in a little bit and talk about some of the potential uses for each of these. But for now, what I want you to do is try some of these out. So we have a plot here, right? This is only 15 particles, and you have to imagine again that there's a little bit of binning going on here, right? This would not be a realistic distribution, but we're kind of truncating some values, and we're saying, okay, everything in this range, that's 2. Everything in this range, that's 4. So keep in mind, there's a little bit of difference from reality there. But we're essentially just going down the list here. We want the most probable speed, we want the average speed, and we want the root mean squared speed. And for reference, I've got those two equations here on the side. So I want you to go ahead and work on this one. So I've got this big nasty chart. They didn't group the first time. That's why I ran into issues. Let me group these again. Let me do this one more time. Let's actually copy that over, and let's come up with a new page here. so we can go ahead and take a look at this. And I don't know how many people can hear my voice slowly going out and collapsing, but that's okay. We're going to make it through this one with the help of lots of fluids. So we've got this nice little graph, and we're going to find all three of these values in order. So what might be helpful for you is if you would like to take each of these and have them written out as numbers. I'm just going to read them directly off of the graph, but I've also done this a couple times now. So the first thing that we're asked to find is the most probable speed. And don't be like me, don't write out most probably speed. Most probable speed. Bam, there it is. Right? 6 meters per second. All I really have to do for that one is look, find the tallest point on the graph, and say, okay, well, if I was to randomly draw these particles from a hat, I would most likely draw from the 6 meters per second, right? Because there's the most of those than anything else. So that was nice and easy. So now let's find the average, which is a little bit less easy. So what we're going to need to do, though, is we're going to need to take this equation. So V average, 1 over n, where n is the total number of particles. And I'll actually be a little bit more rigorous with how I write these things out. So I is equal to 1. We're going to the number of n particles. Every particle has a speed. And whichever particle, right? Or how many particles are at that speed. So when I write out the summation like this, what this really turns into is there are 15 particles in total. There are 2 particles at 2 meters per second. There are 4 particles at 4 meters per second. There are 5 particles at 6 meters per second. And I know I'm doing this a little bit backwards in the order, but it's just how I like to talk about this. I like to talk myself through my problems when I'm doing these, right? And in general. I've got 3 particles and then 1 particle, so that is 3 particles at 8 meters per second, and there is 1 particle going at a whopping 10 meters per second. Which, please don't set your expectations too low for what we're actually going to find for particles. These are all incredibly slow speeds. But anyways, I have a big old thing like that, and it's really kind of obnoxious to deal with. But I do recommend writing these things out, right? I'm only going to ask you to do a problem like this once, maybe a second time or so, because most of the time we don't deal with this few particles, and on top of that, it's really kind of tedious work for not that huge of a solution. It's good to know statistically. It's very good to know how to do this, to understand what the process is. But once you understand what the process is, there are programs that are specifically designed to do this for us. So, you know, I really want you to understand what it is, but then once we know what it is and once we've practiced it once or twice, we can basically say, okay, you know, been there, done that, the computer can do the boring work now. So we would plug all of these in, we sum them all up, we divide by 15 at the very end, and what we should find is something like 5.6 meters per second. So let's go ahead and write it out just in our table. Average speed. .6. Okay, now the last one, right? The kind of odd one out of the bunch, the RMS speed. And that's what I like to abbreviate it as. It's a little bit funky because this is essentially a very similar looking thing. Still a summation, still going to n, starts on the first one, but now it's v squared. And the number of particles at that particular speed, and then at the very end, we'll take the square root of that. So I'm going to start this with a bunch of really big curly brackets, and then I'm going to have my 1 over 15 particles. Then I'm going to have my square brackets. And I'm going to go in the same order, so it's going to be a little bit reversed. But just as before, I say, okay, well, I had 2 particles at 2 meters per second, and that gets squared. And then I have 4 particles at 4 meters per second, and that gets squared. 5 at 6, 3 at 8, and finally 1 at 10. And you can see there's a little bit of a difference with how these go, because think about what the square does to some of these larger values. You're essentially giving a lot more weight to the higher velocity values than you are the lower velocity values. When you do something like this, it's not equally considering all of these particles now. Those higher velocity particles are going to have more pull for the distribution, right? They're going to pull it away from the average into a little bit of a higher value instead. But anyways, we summed this up, and this one is a little bit more annoying. The calculators I see online don't often calculate RMS as often as they do just an average. What you can do with this thing, though, and this is part of why I recommend writing this out, because there's a lot of things to calculate right here. It's really long, so you might instead focus on getting these as individual numbers first, and whatever 5 times 180, so that might be one way you do this, kind of solving this out piece by piece first, and then summing it all up and taking the square root. Just don't trip up over any of the numbers. Don't try and shove it into a calculator all at once. Take it into pieces. But I've done this ahead of time, so when I plug in this value at the very end, I find something like 6.02, and I like that 6.02 just because it really says I didn't just pull the most probable value. This was an actual calculated thing. And that's what we would find for that one. Root mean square speed. But realistically, 6.0. So, I think I've talked about this a little bit before. Square term account for negative velocities. All of these are technically speeds. Technically, if I say velocity, it's only because I see v and my mind immediately thinks velocity. All of these are technically speeds. So there is no negative value. They're all just going to be, they're directionless. So I think I've talked about this before, but when you're thinking about an actual number of particles that you might see in reality, think about one of the smallest things you possibly can have, a tiny particle of dust. If you see that tiny particle of dust floating through the air, maybe, and you wouldn't even normally see it in regular light, right? It's got to be like the perfect angle from the sunlight from the window hits that dust particle perfectly, and you're reminded that you haven't cleaned in a little while. That particle of dust is a few billion atoms. We're not going to see 15 atoms that often, right? I just want to give you a little bit of a sense of scale of what kind of number of atoms we're actually going to be dealing with. Even when we're talking about a fraction of a mole, that's still something like 10 to the 21 atoms, billions of atoms, right? It's not a small value. So taking any of these as actual summations, to do it by hand is ludicrous. To do it by computer is actually still kind of crazy. That's a really big data set to try and deal with. So it's not really practical in any sense to use these once you get up to larger values, but I do want you to get started on the idea of where these things come from, right? They are summations. Any integral is just a summation that's being taken to an infinitely fine comb, right? So when we come to a distribution that looks like this, right, where our fine comb is now infinitely fine, where we actually have to do some calculus to deal with this stuff, know where these values come from, but now we're doing these as integrals rather than as summations. So when we treat them as integrals, or in this first case, a derivative, right, the first thing we can ask is, okay, what's the most probable speed? And that's the highest point on the graph. And if we look at the graph, we can see, okay, well, clearly we hit some peak and then we turn and fall back down. So wherever it flattens out, which is really just, when's the derivative 0? That's one that I recommend solve it for yourself for some practice. It's a good idea, right? Because this is kind of a wacky function, and it's good to have some practice on that. The other two, these are kind of complicated integrals, so I'm not going to ask you to find those. But we basically say, okay, well, all of our possible velocities are anywhere between, or rather, all of our possible speeds are somewhere between 0 and infinity. So we take the whole range, we take the average of all of those, and we should find something like the average speed is the square root of 8 kBt over pi m. And the last one, again, we do the exact same thing, but with root mean squared, and when we take that with root mean squared, we get this equation over here, and this is by far the most important one that we're going to talk about, right? This is the one that we really need to latch on to. These other two, not as important, if I'm being honest. The RMS is really the star of the show this time around. But, you know, there's a little bit of math in that, but that's essentially some way that when you actually take this average out and you plug in with the integrals and you plug in with this distribution function and you find what that value should actually be, it comes out to be this very, very nice clean value. But all of these depend on only two things: the mass per particle and the temperature of the ensemble. And if you've got those two things, you can find your RMS. So, let's try it out. And this is fun because this is applicable, right? This is the air in the room with you right now. Mostly consists of nitrogen, right? Over 60% is nitrogen gas, and then oxygen makes up another very significant portion. So, between the two of them, most of the air is going to be diatomic. So this is all fine, and air is not that much different from the oxygen is not that much different from nitrogen. But let's assume it's at room temperature, so about 20 degrees Celsius. Let's assume that it shares that same Maxwell-Boltzmann distribution. And knowing that information, I want you to find the most probable speed, the average speed, and the RMS. And so as you're finishing up some of these things, I did want to talk a little bit about more to give you guys kind of an explanation for some of the things. I talked about this before a little bit, but when I'm on stream versus when I'm in person, I'm very aware that, for one, I have a tendency to get off on a little bit more tangents. It's kind of I think the nature of sitting at the desk doing this. But for two, it's a little bit harder for me to gauge exactly how everyone is doing on the problems. And I think I have a tendency then to drag on the time a little bit too long. And so I have kind of mentioned that I was going to be doing this, but then I just kind of jumped into doing it. Giving time limits on problems like this, it's not necessarily, how do I want to word this? If you don't get through every single problem by the time I start looking at it, that's okay. Remember that the way that we do these problems is this idea that this is me working alongside of you, right? The order of these steps are that you first read through perusal, right? And you look at the material for the first time, you look at some of their example problems, and you just kind of pick up what you can at the time. I'm not expecting full comprehension from that. So you see that as a first exposure. You come here. I talk about it a second time. I try and answer some of your questions. This should be your second exposure. And this is where we start to work on some of the problems. You start to get a little bit of a sense of how they go. You give it an attempt yourself. And there's two things that I would like to do by putting some sort of time limit on these problems. The first being that, of course, we keep the lecture on track and I can get through all the material in the day and we don't have to drag over anything else like that. But the second one, I really want to try and, I think I would like to do this even if we had an infinite amount of time. I think I would like to put a time limit on things anyways, because I don't want you to overthink the process that you're taking. If you're trying these out and you are following symbolic solving and everything else like that, and everything that I recommend for solving, you don't have to get these right every single time, right? And that's part of why I like to give you the solutions to the problems that I'm asking you about immediately, because that just tells me that as long as you have either worked through the problem yourself or you have watched me work through the problem, one way or the other, you have gained a little bit of exposure of how to go through the problems and how to solve the problems. And if you don't get them right the first time, that's okay. Just try and, follow the path as well as you can and see what you can do with matching things. If you are on step 1 of 4 and you're not really certain, but you think you need this value and you don't know if you got it right, then don't overthink it, right? Say, okay, well, this is what I got for part 1. I'm going to take that on to part 2. And if I'm solving symbolically, then hopefully it's pretty easy for you to go back and say, okay, well, maybe I didn't do part 1 quite right. But if I take this corrected solution now, well, parts 2, 3, and 4 were correct, in my thinking. I fixed part 1 and I've got this down now. So I say this as kind of an explanation of where I'm coming from with this, what my reasoning is for going along with these time limits on problems now. But also, kind of a reminder, don't overthink these things too much. We're working through these for practice right now. But anyways, let's go ahead and do that practice. Let's go ahead and solve this one together. So we know what kind of particle we're dealing with here. We've got a temperature for this thing, and by the fact that we are a Maxwell-Boltzmann distribution, we've got these equations, right? So we'll use these in order. What we're going to do is, let me switch over to this one. Let's find ourselves a little bit of space, right? Let's do it over here. All I really need to do is plug these things in. I know that nitrogen gas has a mass of 28 atomic mass units. I need to convert that into kilograms. And so using the conversion that was on the screen right there, this should go into 4.65 times 10 to the negative 26th kilograms. And that is the mass per particle, mass per molecule, rather. Temperature, 20 degrees Celsius. It's not a delta T, though, so I really care about having this in Kelvin. 293 Kelvin. And then I can go down the list, essentially. Most probable speed, 2 kBT over m. Plug and chug. 417 meters per second. Average velocity, 8 kBT divided by pi times m. And the pi might look a little bit strange at first, but that shows up when you do the integral in that certain way. Pi is one of those values that shows up in weird places all the time. When exponents get involved, pi is usually there as well. So we plug that in, though, and what we find is 470 meters per second. And I want to take a pause right here. And I want you to think about what values I just wrote down. I'm trying to tell you that an atom flying around in this room with me right now, on average, is going at 470 meters per second. The speed of sound is 343 meters per second. But I'm also going to say this is accurate, actually. And in fact, this is on the slow end. Because if I'm only assuming that there's nitrogen and oxygen, then they're going to be approximately these speeds. But if I actually consider that there might be some lighter particles in the air as well, maybe argon, that's going to be moving at an even faster speed. If there's a little bit of hydrogen in the room, I would expect those to be moving around 1,500, 1,800 meters per second. They're fast. They're really fast. So if all of these particles are so fast, why don't I just get bumped around while I'm moving? Like every single time, I have to assume these are colliding with me all over the place. Why am I not just getting bumped around every which way? It's not just the difference in mass, actually. That is some of it, certainly, but it's not all of it. What it actually is that I want you to, again, think about how many particles there are. Because it's not just that there's a difference in mass. Because if you go outside and a gust of wind blows, you feel that force, right? That's essentially when you have this blanket of particles all moving in the same direction for just a little while, and you feel some sort of net force because of that. So certainly, it's not just the mass difference, but it's that you're surrounded by these particles. You're feeling these collisions from every direction, constantly. At any given moment, you are experiencing billions of collisions with all of these particles surrounding you. And remember, it doesn't matter how many forces are going any which way. Because if I even think about this, if I think about, like, let's assume that I have, say, 1 square meter is one side of my body. Then the pressure coming from that, 101,325 pascals, times the surface area that it would be applying over 1 square meter would mean that there's about 100,000 newtons of force on any one direction of me. But I feel that from all sides. That's not just from any one side, that's coming from all sides at once. And when that's coming from all sides at once, statistically, I'm under zero net force. And this is a really kind of fun thing, though, because, and I've brought this up before, that realistically, we don't use average velocity that often. We sometimes do, but not that often. One such use, and I like to go off on this tangent all the time, is the research that I used to do with the cold atom lab. So when you're doing something with cold atoms, and there are many different experiments that you can do with these, but when you're doing an experiment with the cold atoms, you have about 100 million atoms at most, right? And compare that to what I said, that a dust particle has a few billion. So less atoms than a dust particle. We always brag that it's the smallest amount of anything you'll ever see. But how do you measure that with a thermometer? You really can't, right? Because for one, if this thing is supposed to be incredibly cold, well, the thermometer is going to get in there and really heat it up. For two, it's in a sealed vacuum chamber, so it's a tough time getting in there with anything. But then for three, how do you measure the temperature of anything so incredibly small like that? You really can't. But one thing that you could do is you could observe how fast those particles are moving if you're very clever with it. And so what we would do is we have our ball of atoms held in place by a bunch of lasers. For a brief moment, we turn everything off and we let them fall. And they're falling slow enough that you can watch it happen on a camera, right? Gravity is a real effect to them. They're not just bouncing every which way, but you can watch them fall under the force of gravity, and then you flash the lights on again real quick, and you measure how far they fell. And based on their average velocity, they spread out like a Gaussian distribution, like a bell curve. And if you take that spread and you find the average velocity, you can use that to turn around and find what the temperature of those particles would be. And we calculate that they're at about 40 microkelvin. Now, we're not going to use V average in a lot of our calculations, but it does occasionally have some use like that, right? Instead, what we're much more frequently going to use is the VRMS, which is a 3 kBT over M. Right, but it's a fun use of average temperature, and I love to go off on that tangent all the time. You'll hear more about that, I'm sure. Science is cool. Newsflash. But when we plug in for the VRMS, our final answer here should be 511 meters per second. So the VRMS, you can kind of see, it's always going to be a little bit higher than the average velocity because, again, those larger velocities get a greater weight in the distribution, right, when we're actually doing that calculation. And so they're going to kind of pull it away from right in the middle. They're going to pull it to a little bit of a higher value for the VRMS. So we've talked about VRMS, and I keep telling you it's useful. And I'm going to give you another variable that I'm just going to say is useful, right? And we'll talk about why in just a little bit, though. So this other value is called the mean free path. So it's basically how far can a particle go before it smacks into another particle, right? So what this really depends on is just the number density, which is a little bit unique because you might at first think, okay, well, there should be a temperature difference because if they're moving all around in every which way, then they'll bump into each other more often. But this isn't actually a measure of how often they bump into each other. It's how far in one direction can I go before I reach another collision. So it looks like this, right? Lambda is equal to 1 over 4 square root 2 times pi times number density times radius squared. So keep in mind, 2 is the only thing that's in the square root there. I've seen a little bit of confusion on that one. But, and then we take n over v as if it's its own value, right? That right there, number density, is some value that we can actually calculate. And then the radius that you're going to use, this is essentially where we start this divide between describing all monatomic and all diatomic gases as if everything in that category is identical, right? And I've kind of already done that a little bit, but not so much yet. Here, chapter 20 is where we're really just going to say, okay, forget the fact that there are slight differences. Oxygen and nitrogen and fluoride, they're all technically slightly different in their radii, but you know what? They're so close. I might as well just group them together. So we've got those two values down here, 0.5 times 10 to the negative 10th and 1 times 10 to the negative 10th as the two radii that we might use in this. So we can immediately throw this into a problem, actually. Let's say that we're talking about this room air once again, right? So it's nitrogen, it's at atmospheric pressure, and it's at 20 degrees Celsius. What I want you to do here is find that number density first. I know I've put it as part B, but something possessed me to put that as part B rather than part A. You need to find the number density first, and then you need to find the mean free path. And I'm going to bring up this equation that we haven't seen in some time now, this other form of the ideal gas law that we can actually use. This version is very, very, very useful because it immediately has N and V, right? So we can find the number density from that equation right down there. It's a very useful way to do this. That's what I recommend. It's an equivalent equation, right? It means the exact same thing. You can solve out the Boltzmann constant from Avogadro's number and that ideal gas constant, but that's all kind of mixed in there together. So find that number density, find the mean free path, and then let's compare. Another note that I should bring up here, this is not anything to do with the problem, but more for the lectures. So it takes me a little bit of time to actually get the lectures edited, right? And I think that's worth the value because I end up trimming off significant portions of time from that so that I know there are a few people that go back to lectures and watch them again, if not for the first time. So I see it as a time spent to save you guys a lot of time that is very worthwhile to spend a little bit of time editing. As I start to do this on Twitch, if you would immediately like to go back to any of the lectures, Twitch does save them for 2 weeks, but it saves them kind of exactly as they were. So there's still going to be these large gaps of time, whether we're taking a break or whether I'm giving you guys some time to work on problems. It's very untrimmed in that sense. So it might be a little bit excessively long. It'll also have both lectures kind of stacked together as one whole big thing. So that's a way that you can go back and view the lectures immediately if you don't want to wait for me to finish editing and uploading. But, I figured I would just kind of bring that up for anyone, again, there's options for however you would like to view these things. So we're expecting two things. One, it's going to be a very, very large number density. Two, it's going to be a very, very, very tiny mean free path, right? They go inverse with each other. So that's the equation I'm going to need, right? So let's write that down first and let's figure out what pieces we need from that. So lambda And I'm going to write the denominator first. 4 root 2 times pi times number density times r squared. All of that under 1. And I also know that r is 10 to the negative 10th meters, right? It's a really tiny amount. So what I'm really going to need to do here, since I already have r, I really just need to find number density. I'm going to take that ideal gas law, and I'm going to take what we call the physicist version of it in KBT, mostly because this already has N and V in it, right? So I can do a little bit of rearranging on this. Number density is equal to P over KBT. Pressure is supposed to be 1 atmosphere. In standard units is 101,325 pascals. Temperature is supposed to be 20 degrees Celsius, which we also know as 293 Kelvin. Plug them in. And when we do that, I find a number density, something like, let me actually look this up. The number density that I find is something like 2.505 times 10 to the 25th. And then I write these units in a little bit of a strange way. I write these as number per cubic meter. And I do this because it's more of a placeholder than anything. The actual units are per cubic meter. So nothing per cubic meter, because number doesn't have a unit. But when I talk about stuff like number density and everything else, it helps me to remind myself that this is a number density. And so sometimes for units like this, I'll just put essentially number in place per cubic meter. It just helps keep track of things for me, right? That's what I like to do, at least. Anyways, once we have that in place, we've got our value for the number density. We have our values. We've got everything, really, right? We're ready to just plug stuff in. And when I do plug stuff in, I should find something like 2.246 times 10 to the negative 7th meters. Only slightly less jammed up than New York traffic. Right? It's a really tiny amount, though. It's like incredibly small. There's very little space that you can move. Do keep in mind that these particles on average are a little bit less than a nanometer. So, you know, they are moving their own length a few hundred times over before they run into something else. But it is still a very tiny distance that they can actually travel before they run into something. I also have a special notation note. I use this. I love it. I don't know how many other people use this. Anytime I do square roots, and you might have noticed this before, but I always end my square roots with this like little overhanging bit. That tells you where the end of the square root is. I just find it helps me for notation. It helps me keep track of where the square root ends and we multiply other stuff, right? So 2 is the only thing actually under the square root here. I think I found this and somebody had wrote it in the margin of like a textbook that I rented from the library. And I loved it, and I've adopted it ever since, but I don't know many other people. It hasn't really caught on, unfortunately. I think it makes things a little bit more clear, but I just want to kind of point that out to really emphasize that the square root ends over the 2, and that's how I draw that to kind of signify that. But let's go ahead and look at the secret part B. And by the secret part B, I mean it was on the next slide down. So integrated circuits, right? When you're talking about things like processors and graphics cards and any of these circuits that are drawn on incredibly tiny pieces of silicon, on the order of, I think, commercially available now, computer processors go down to 7 nanometers is essentially the width of the wires. It's incredibly small. But when you are dealing with things that are so incredibly small and precise, air's a big deal. air gets in the way a lot. So you manufacture these often in clean rooms, and then you have a vacuum chamber inside of the clean room. So the vacuum chamber, expect a pressure of something like 1.1 times 10 to the negative 10th millimeters of mercury. Keep in mind, that's a pressure unit that we haven't seen for a while, but there is a conversion for that. So let's do the same problem over again, but now with this new pressure, and I'm going to say it's mostly nitrogen again and assume that it's still at room temperature. But let's find these values now that we're at this super crazy low pressure. So let's go ahead and take a look at this one. Really, the trick is we've got to convert our pressure, and it's a new pressure. But otherwise, the temperature is going to be the same, the particle is going to be the same, so those two values are going to stay constant between these two. I messed up when I wrote my solutions for this in the first place. I didn't have the right number in here, so I'm going to have to be looking back to the old slide because I did it there. But the conversion that we can do for this is that in 1 atmosphere, there is 760 milligrams mercury. And when we do it like that, that should come out to be a number something like 1.47 times 10 to the negative 8th pascals. So, it's a little different, right? What's factor 15 between friends, though? So, we're going to go through the exact same process again with finding that number density. We say that number density is equal to 2P over kBT. We assume it's the same temperature. It seems reasonable, right? It's still a room. And what we would find now is that 3.627 times 10 to the 12th again, I like to write number per cubic meter. Just helps remind me that it's a number density. So it looks like a lot, right? But then you go back and you compare this to what we had just seen before, and that's a pretty substantial difference. So we go through and we plug it in again, right? Lambda in the exact same way. We just plug in all of those numbers again. And what we find this time around is actually 1.55 times 10 to the 6th meters. Or 1,500 kilometers. That's not a tiny amount, right? This is actually in the range of one of our ideal cases. And that ideal case is what we would call a collisionless gas. And of course, there's not a such thing as a collisionless gas. But when collisions are this infrequent compared to the size of the particle, we might as well say, okay, well, like, you know, imagine how many collisions actually happen over the lifetime of this gas. It's nothing. It is completely unsubstantial. And there are a couple equations and a couple idealized circumstances that we like to use where we call it a collisionless gas. It's not anything that we'll really get into in this course, but it is a special circumstance that we sometimes like to use. But yeah, it's a pretty crazy large value. And however much it changes, but circumstantially, when you're actually dealing with vacuum chambers and clean rooms and stuff like that, almost all the gas that you actually find in there is not actually going to be nitrogen. It turns out, you know, nitrogen is huge on the scale of particles in air. What you're actually much more likely to find is helium. Helium gets in the way a lot of different sorts of vacuum chamber applications because helium is so incredibly tiny because it's monatomic and it's the smallest monatomic gas. It gets in everywhere. Luckily for us, there's not much helium in the atmosphere, but the helium that is in the atmosphere, it gets in everywhere. You can't keep it out from anything. So most vacuum chambers that you would ever see constantly have vacuum pumps running to try and pull out that excess helium. along with other things. There are a number of things that can contribute to pressure inside of a vacuum chamber. But yeah, it's something. So here's where we really kind of tie these two descriptions together. Right? Here's this idea that I have talked about this before, where pressure is essentially a result of all of the atoms colliding with each other and colliding with the walls of the container. Right? When we consider it like that, every single time one of these particles collides with the outside, what's really happening here is you have some sort of collision, right? And we describe collisions with momentum. So, unlike balls of clay, atoms are not going to dent when they collide with each other. We can assume that all of these collisions between particles and the walls of the container are going to be perfectly elastic collisions. Momentum is conserved, energy is conserved, and when that happens, we've got some results that go into this from people much smarter than me. We're not going to work through this derivation, but sufficient to say that if you take it over some period of time, then the pressure is a result of, well, mvrms squared. There's a derivation that goes into this that essentially averages out the number of collisions that you would expect to see in any unit time, the momentum change because of those collisions, and you can find the pressure because of that, or really the force per unit area because of those collisions. So, and again, it only really depends on number density. There's a little bit of dependence on the mass here because, of course, the particles themselves have mass. Yeah, this is another way that we can essentially describe what the pressure of a system would be given not state variables anymore, but microscopic descriptions. So I think that's kind of a neat thing, and especially because the number density is not something that's necessarily tied to any one container, right? You could essentially calculate the pressure given a small sample size without needing to take a full large volume because you really just need that number density. That's the really important part here. The much cooler one, in my opinion, though, is temperature, right? And I keep using this description that temperature is really how much are the atoms buzzing around, and this is where I'm going to finally prove it. If we take one particle, one single particle, we can say, okay, well, that particle has a kinetic energy based on its speed, right? 1/2 mv squared. Blast to the past, 191 material coming back to haunt us, right? Say, okay, well, that's great for one particle, but once again, I have billions of particles, so I need some easier way to describe this. Well, if you were to take the average energy per particle, then a weighted average of that, 1/2 mv squared, you need an average based on v squared, you really need 1/2 mv RMS squared. So this is one of the reasons why I keep saying that VRMS is really the important thing here, because it shows up in temperature and it shows up in pressure, and it shows up everywhere. It's really what we need to use for a lot of these things. Average velocity is unfortunately just not that useful for us. RMS is really where it's at. But if we go back to that pressure description, so we take what we have, the average energy of a particle is 1/2 VRMS squared. Then we say, okay, well, let's go back to pressure. Let's plug in with what I just found, right? I recognize that there's a mvrms squared here. So I can plug that in, and I can really say that pressure could be a function of average kinetic energy of the particles. And let's take that a step further. Let's go back to our ideal gas equation and say, okay, well, I know PV in kBT. Let me rearrange this a little bit. And I can turn this into 2/3 average kinetic energy per particle is equal to kBT, or the average energy of a gas per particle is 3/2 kBT. And this is a really cool description, because I want you to think about this for a little bit. What this really is saying, that this is our definition of temperature. This is our description of exactly how we would find temperature given the average energy per particle, or rather, we could find the average energy per particle based on temperature alone. Mass and the VRMS are all wrapped up in this thing, right? And it's a really cool description because what that means is that different gases at the same temperature won't act exactly the same way, right? We can see that if the temperature between two gases are the same, that really means that the average energy per particle is going to be the exact same, right? Whether it's helium or whether it's the heaviest gas you could possibly find, I don't know, rubidium vapor, cesium vapor, something really, really heavy, right? Those velocities might change. The VRMS will be different for those two gases, but as a whole, when you look at them like that, you can see that the average energy per particle, if they're at the same temperature, is going to be the exact same. So this works really well with our description of temperature as well, because when we talked about temperature the first time, we said, okay, well, we know that if two objects at different temperatures are allowed to be in contact, heat is exchanged. And this is why. Because all of those particles are going to interact together until there is uniform energy across both sets. So there's some really fascinating revelations built into this thing. And we're going to make this really crazy next time, because I want you to think about this. What I've just done here is I've described translational kinetic energy. And I realize some of our terms might be a bit rusty here. But is there another type of kinetic energy? There is indeed rotational kinetic energy. And that's not accounted for here. But we'll get back to that. We've got to kind of discuss what goes into this. There's some weirdness that we're going to approach next time around. For now, 3/2 kBT, that's sufficient. So, let's use this. This is kind of a short problem, actually. But I want you to find what factor does the RMS speed of some random molecules increase if I start from 10 degrees Celsius and I heat them up until they're at 1,000 degrees Celsius. What factor does that RMS speed change? So, one thing with this that might make this a little bit easier, I'm going to call the VRMS first one and the second one. I'm just going to call that V1, V2. Let's remember that it's VRMS. 10 degrees Celsius, which really should be 283 Kelvin. 1,000 degrees Celsius, not a factor of 100. Absolute scales, right? Please don't forget that. So this will turn into 1,273 Kelvin. Okay, so what we're going to need to do, it's kind of short if we actually put everything together the right way, but let's just go ahead and be a little bit rigorous with it. You know, no harm in doing that. So we have to be in Kelvin. We also should remember that our description that we have here, average kinetic energy per particle, right? So let's call this E1, for example. 1/2 m V1 squared. Keep in mind, again, this is a VRMS. It's just for the first one. It's easier for everyone if I drop some of the subscripts in favor of others. This also happens to be equal to 3/2 kBT. And specifically here, T1. I can rearrange this a little bit, right? I want to know essentially how do these VRMSs compare. What's the ratio if I plug those two things in together? So what I'm going to do is I'm going to solve out for VRMS, or V1 here. So I'm going to say V1 is equal to, and I can cancel out that, I can cancel out that, and then I just have to rearrange the rest of it. So it's going to be a square root 3 kB T1 over M. Okay, and I can actually do the exact same thing for V2, right? Like this isn't going to change, it just changes the subscripts. So V2 is going to be equal to square root of 3 kBT2 over M, and we say it's the same gas, which is a very important point. If this was a different random gas at 1,000 degrees Celsius, keep in mind we couldn't do this the same way anymore because M1 would be different from M2. So everything would go off, right? But as long as it's the same gas we're heating up the entire time, it's the same M, we're safe. So now I'm going to try and combine these together. I want to find, essentially, V2 over V1. When I do that, you can kind of already predict what's going to happen here, right? There's a lot of things that are going to cancel out. I'm going through all the steps here, but if you saw this earlier, you could really kind of jump through a few of these and skip a lot of it pretty early on. 3 kV, that's all going to cancel out. What I'm really left with, this factor is the square root of T2 over T1. If we plug in the numbers as we've got them, 2.121. That's our final answer. That will conclude 20-1. Next time we'll pick this back up at 20-2. We'll talk about some of those pesky things like rotational kinetic energy and all the other weird stuff that's going to make these things complicated.